So, this tutorial, we're going to be talking about how to effectively debug your code because I think you should already be in a stage where you tried some debugging, some work, some may not work. Debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. And that's why we will need to learn about effectively debugging techniques. Why debugging matters? There will be bugs, even if you write your code in the most clever way, in the most careful way, there will be bugs. Debugging and testing takes 50% of software development time. This will take even more for hardware. Usually in industry, it's about more than 70%. This is not just for software, for any complex system, like hardware, like cars, like radios, wireless communication. Debugging is a learned skill. You can learn to debug effectively. The more you debug, the better you are at debugging. The system is not magic. You should be understanding it. In order to debug it, you should be understanding it. You don't have to understand the entire thing. You just have to understand the part of the code that could have the bug. Debugging can be deeply rewarding if you are debugging with the correct mindset. It should be driven by curiosity and creativity, and you will get a lot of satisfaction if you can understand a bug's root cause. If you just want to complete this task and debug it, it will be really torturing. But you will be satisfied when you actually find this bug's root cause and fix it. So today we're going to be talking about systematic approaches to debugging. There are the infection model, the Wolfman's algorithm, and the detective method. We would expect you naturally will use a combination of all three to debug. We'll then do an interactive debugging demo by debugging the same function that we wrote the last two tutorials with you, and we will end with a team debugging activity. And given the number of students we have, I guess I'll just let you debug on your own for a few minutes and then we can do it together. All right. Infection model. Software systems are causal. So are many other types of systems. Anyone knows what is the definition for causal? You will learn more about this word, this terminology in system control. Causal means the current state of the system is dependent on some previous state in time. So the system is sequential. It is dependent on what happened in some previous time. And that means what happens in this current time will affect what will happen in the future. A faulty operation causes an infection somewhere in your code. This faulty operation will be one single place at first. And because the system is causal, this infection will spread through the program state silently until it eventually causes an observable failure. It's either a crash or it's printing some wrong value or it's returning some wrong answer. And so when we're debugging, we want to identify this observed failure as soon as possible before it actually spreads around in the program state, and that will make it really hard to find the root cause. One technique to do it is called the wolf fence algorithm. And it's and the idea is how to find the wolf in Alaska. what we do is we put fences. We want to make sure that one side of the fence does not have the wolf, so we can eliminate one side of the fence. Then we put on more fences, we eliminate more sides until we are at this really small point. And then we can actually look at the code and find the wolf. In debugging the program, we want to, after we see the observed failure, we want to put on fences. We want to make sure that one side of the fence doesn't have anything. And this is some point in time. It does not have to be where the bug just happens. We just want to identify some time in time that this program state is correct. So we can say that the bug happened afterwards. Then we can put on another fence to isolate out some other variables. And then we're left with this small program state that we can actually go into the code and start staring at it. We don't want to start staring at the entire code because it's going to take a lot of time. We just want to narrow it down. And we want to start from the observed failure. We want to get all of the states that is leading to it, and we want to find which state is the problem. We want to systematically eliminate the possible causes to get the most information for least effort. And this approach actually utilizes both the wolf fence and the causal control flow of the program. Yep. What is this tutorial about? This tutorial is about effectively debugging. So it's not about milestone. It's about milestone 1 and 2 in general. The next tutorial is about milestone 2, and it's a really important one. The method that is the most widely used is called the detective or scientific method. So it follows a general flow. We first observe the failure is either a crash or some wrong answer that's outputted in std out or std error. We want to first make a hypothesis on what could be the root cause. Such as if you see a seg fault, then you probably should be suggesting that it's some memory access out of bounds. If we guess, after we make this educated guess at hypothesis, we can then predict if this hypothesis is correct, then what should happen if I do this, if I do that. Then we make the experiment to validate this hypothesis. We make the observation either from the outputs or by inspecting variables with the debugger. We want to verify whether this hypothesis is correct. If it's not, then we make another hypothesis, and so on. The hardest part in this flow is actually generating good hypotheses. The hypothesis goals are to make them easily testable, to make them quickly lead to the root cause. Like seeing seg fault means there is a memory access out of bounds, invalid memory access. Or if you can see something that's like double freeing, you'll know that it's related to some pointer double freeing or something like that. And the ability of making good hypotheses is actually a skill that can improve greatly with experience. After you see a lot of root causes, you'll be able to generate good hypotheses. Let's do a debugging walkthrough using the same function that we wrote from the last few tutorials. Remember the global variable that we make is a vector of ints that looks like this. And we have our loading helper function and the actual function that does the return here. Let's get into the demo. I'll go into my tutorials. So this is my repo folder. I want to do a make clean. I want to do a make configuration equals release. We want to know what is the problem with this code. And I will do ECE297 exercise 1. Let me see. We'll just wait for the test to finish. Because in this code, we only implemented that one single function, so we're expecting to see only one test passing, and now it's failing. So we want to know what is the problem. So we want to narrow it down to only run that tester, run tester, functionality, intersections. You see 3 of 3 failed, and if we scroll up, we see this is intersection street segments, unhandled exception test crashed. And right after that is the second test suite. So there's only one error message for the first test. And it doesn't give us anything. It just gives us unhandled exception test crashed. So let's download the tester file using debug tester. Debug tester. It says recompile the project in your IDE using unit test configurations to debug. To run valgrind, there is this command. Let's open the code. Go to makefile. I want to compile using unit test. Before compiling using unit test, let me go into the actual test file and delete the 2 tests that we don't care about. That is starting from here. This is the local version of the tester file, so you can modify us in any way as you want. So I will do configuration unit test debug. I will build all of the targets. I will set the launch target to test libstreetmap. That is the executable to run the auto tester. If I just run it, I will get the exact same message. Unhandled exception has crashed. Failure 1 out of 1 test failed. Now let me run valgrind. I will just copy and paste this entire command. Copy and paste. So this entire command will run the exact tester file after we did the compilation in the IDE. And as you can see, it's slow. You need to just wait for it. So as you should already know, it checks for memory leaks. It checks for heap summary, and it checks for invalid read or writes. The one we really worry about is the first one. And as you can see, the length is already exceeding the buffer length of this terminal. So what we should do is something like this. I want to do a t out while grind dot log. This is the command to both see the outputs from the terminal and to key this output into this log file. We should be waiting for it to finish again. T is just the command name. So if you do this and then a file name, this will both print to stdout and print to this file. There is also another command that can redirect all of the outputs to a file. You can choose whichever one you want. This command is useful because you can both see both, right? All right. Let's just gvin that file grind. You can also see it in VS Code, but I like them more. So I want to go to the beginning by pressing GG. And the first error is an invalid read of size 8. You can see it's some vector. So what is size 8 in this case? What is size 8? It says invalid read of size 8. Is that index 8 or is that something else?
I guess it's fine.
The vector size is 8. Valgrind doesn't see the vector size. The sizes Valgrind is reporting is in bytes.
So it's the size of whatever.
Yeah, it's the size of whatever you're trying to read. You're trying to read something that's 8 bytes. So what is 8 bytes? We know that we have a vector of int. And what is the size for integer? 4 bytes. So it's not reading an integer. It's reading a size 8. And what is of size 8? A double? But we don't have doubles. Size 4 is 32 bits. Size 8 is 64 bits. We're in a 64-bit system, so we're reading actually an address of size 8. Because it says it's in the vector, and we only have a vector of int. We're not reading integer, the only thing we can read is the address. So we're trying to access something that's in the outer vector, because the outer vector stores addresses. The inner vector stores integers. That's already one hint. And we get that from experience. If you don't have enough experience, it's just telling you we're reading something that doesn't belong to you. And we can also jump to the end by hitting Shift G. There's some Vim commands. Okay. Since we know it's a memory issue, there's another way of testing for memory. We want to go to unit has debug check, and everything else stays the same. We do build clean. Then we don't have to open Valgrind. We can directly run it because it's already compiled with debug check. You see, this is much faster than Valgrind. And it actually exits at the first invalid read or write. So this saves a lot of time than running Valgrind. Let's see what this gives us. It gives us this error message. So from here, we know it's again about something about vectors. And here we're saying attempt to subscript container with out of bounds index 1, but container only holds one element. It still doesn't tell us much, but at least we know it's a one element container and we're trying to access with index 1. Now, because this program crashes, there is an even better way of attempting this. We want to do unit test debug. We want to do build clean. And without setting any breakpoints, we debug. We enter the debug mode. And we wait for it to segfault. The debugger will pause whenever it segfaults. So let me remove this one. So what you should see is this. We have variables, we have watches. Watches should initially be empty, and we have the call stack. Under the call stack, we want to skip over all of the STD ones. We want to click on the actual function that you wrote, and this points us to the exact line where it segfaults. And in the debugger, you can check all of the variables here, or you can hover over each variable to see what is each value. So we have SSID 0 intersection 1. That is the index that we're trying to subscribing. And we have this vector. Remember from debug check, it tells us it's trying to subscribe a container with size 1 with index 1. We already see the index 1, and let's just make sure that this is the container that we're talking about. We want to go into watch, add, expression, and I will say intersection, street, segments, dot size. Let's see how many elements this vector holds. 1. And that exactly matches with what debug check tells us. So for some reason, this container only holds one element and we want to access the second element and it seg faults. It crashes. Why is that? This is where we should be setting a breakpoint. We want to watch for this watch as we go. Let's restart. It restarted and it entered this function. Then we want to do step overs. So we just did a pushback that incremented this size to 1 and continue on stepping over. The first iteration finished, and now we're at intersection equals 1. And this size never incremented, and we are at this line. So can anyone see how should we fix this? We should be adding the new element somehow. And from our discussion with vectors, we know that pushbacks are slightly less efficient than resizing. So we want to remove this pushback. So if you just click on the stop, it will still show you the code at the same place. And that's a pretty good thing. So we want to change this pushback that changes the size from 0 to 1 to resize. Because we already know the size that we want. And the size is the non-intersection. And now this empty vector is never used anywhere else, and it's safe to delete it. And now I want to, actually, I didn't. One has passed. And we're done. Yeah, resize has 3 usage. The first, or 2 usage. The first usage, if you just give it the size, it will just resize, allocate that much memory, and it will just not initialize anything. Or you can give it a size or initialize value, and it will resize and it will fill the vector with that value. So it has 2 usages. And using resize is just slightly more efficient than pushbacks. If you already know the length of this vector. All right. Any questions so far? If you want to debug something else, the debugger is also helpful to also tell you where this value goes wrong. Team debugging activity. So we want to give you argument sorter code. What it does is on the command line, we call this program using argsort and some number of numbers. And we want this program to give us the output of a sorted list of numbers in ascending order. This is the code that we will be giving you. We have the main function. In the main function, we read in from arguments. We call this shell sort function, and we output. How the arguments work in C++ is argc is the argument count. It gives us 4 for the 4 arguments. Argv is the argument values. Argv is in arrays of characters, which means argv is in strings. The first argument is always the program name, and then there are the other arguments going in. Let's go on to this URL and let's try debugging. Go to it. So this is online IDE that supports debugger. And you can put in the command line arguments here, like 613. And if we run it, we will see the output is nothing. And we can also put on breakpoints like this, and we can also enter the debugger. This debugger is operated using GDB. So we can start with, it will go to one breakpoint and will show where we are here. And we can step over, and now we can do probing of variables, or we can just see the variables here. If you want to set watches like vec.size, we do p vec.size. This will give us the current vector size. And let's try debugging this program and see what's wrong. There might be more than one bug in this program. I will pause recording. Just tell me when you're ready to debug it together. Now. All right, let's go to here. So if we want to put a wall fence here somewhere, what should be the best place to put it? Before we enter shell sort, because we want to first validate that vec is correct before we actually enter this really hard function. So we'll just put a breakpoint somewhere before it. And let's enter debug. And let's start the debugger. And we should see that vec is here. And we can actually already see the value now. Vec has a length of 0 and capacity of 0. And that's already something wrong. So we put a wall fence and we can now ignore everything after the shell sort call. We want to focus on the code before. So now let's put a breakpoint here and let's see step by step what is wrong. So let's stop the debugger. We restart the debugger. And now let's do a step over. step over. We see now that the vec is still of size 0, and size 0. Let's redo it again. Step over, step over. And we're already in some iterations of this for loop, but vec is still of size 0. So what is wrong? Yeah.
Isn't that we're not actually inserting the value into the?
Yeah, so we're reading the value in like this, but we're never inserting it into the vector. So we have to stop the debugger. And we want to do vet.pushback. B. All right. Let's run it now to see if it's fixed. So our arguments are 613, but if we run this program, we got 016. So we get an extra 0 and we are missing the 3 somehow, right? So now let's put this wolf fence here and let's see whether this problem happened before or after we call this shell sort. Enter the debugger again. Start, and we pause at this breakpoint. We see vec is a vector of length 3, capacity 4, and it contains 0, 6, 1. Or we can also see it by doing p vec 0, 0, or we can do vec 0 here. Anything will just work. Anything will just work. So what could be wrong? Again, let's stop this debugger and let's still do a single step over, starting from the beginning. At the first pushback, which is where we actually push back the 0, we see we are getting the value of 0. And I is 0. Then we step over, we're at I equals 1, and we're reading in the 6. Then we do I equals 2, and we're reading in the 1. And then we exit this for before actually reading in the 3. We'll see the argument list is 613. So what could be the problem? We're reading, yeah.
Is it the index of argument reading that we start reading from? Because we start reading from index 0. By the time I reaches the end of the condition, you have an argument that isn't embedded.
We're reading from index 0, and for some reason, index 0 is giving us value 0, and we're missing the last argument. So the reason is, if we go back to the slides, the argument count is 4 in this case. And argument 0 is this program name that is a string. And then we have our actual argument 613. So we should skip over the program name and start from index 1. Then we read the 3 numbers, yeah.
I understand that, but why does the argument turn into a zero when you try to read it as a, I think we're trying to read it as an integer. Why wouldn't that cause a type error instead?
Because this is what we're doing. We're converting this string into a string stream. We're then using this string stream to write into the integer v. So what string stream sees this is whenever it sees this operator, it will separate our string into space by spaces. So each space will just separate out two strings. And this will just read the first string. This will just read the first string. And because that string is a string, like it's a name, it's not a number, what this will do is naturally change it to a zero.
Why would that function, why? Would,
That's just how string streams are.
wouldn't it be more useful if it just, like, threw an error? Like you're trying to read a string into a,
Into a
you're
number?
trying into a double or into an int, because that, like, I know it's just complaining, but that seems like a bit tedious, like that it just defaults to zero. Yeah.
That's a really reasonable comment because this is how string streams are implemented in STL. And in STL, they want to make it stable. So if string streams just randomly fails whenever it reads something that's not making sense, it's just their design choice to keep it like this.
I thought, like, when it reads something, it can't read it, it breaks like the fail.
It can read it. It actually parses it into zero.
Like when we learned about string streams, or maybe that was like finance. They said like if the stream tries to read something that's like invalid basically, then it'll raise like a failure from.
If we read using scanf, then that's the case. If we do scanf, then we have to specify the type and then it will fail if it's reading something invalid. But I think this operator will just silently read something that's not making any sense. I think that's how it's done. At least StreamStream does it this way. And it also depends on compilers, the system, and the C++ version that we're running. So then, back to our debugging exercise, we want to then start from index 1, and we want to read all the way up to 0, 1, 2, 3. So we want to read 1, 2, 3. argc should be 4. And then now we're doing I less than argc minus 1. So we want to read all the way up to 3, but now it's reading up to 2. So we want to remove this minus 1 as well. Let's run it. 1, 3, 6. And let's randomly add more to it. Run it. Let's add one more, just to make sure it still works. It works. And let's add some values that are the same. Let's see if it still works. still works. Let's add something that's 0 minus 1. Still works. So we tested enough corner cases to make sure that this works. And as you should already notice, we didn't really need to enter this entire function to fix all of the bugs because we fenced it out. And this shell sort function is actually correct, even if it's not written in the best coding style ever. It's really hard to read, but it's actually correct. All right. What approaches did you just use? We just used the wall fence method to fence out the entire complex function. We just focused on the for loop before it. Do we need to carefully read all of the code? Reading all of the code is not the most efficient approach. We want to fence out a lot of things before we actually carefully read some small code segments. We use the wall fence to fence out the function. Infection model, we want to fence out whatever is afterwards as early as possible because we want to identify the first occurrence of the bug. And because by infection model that bug will be propagating afterwards. So we want to fence out of whatever is afterwards as early as possible. After we finish the first one bug and we make sure that the first code segment is clear, we can start fencing out other things if there are other bugs remaining. Did we do hypothesis testing? So after we see there is a 0, there is a missing 3, we are hypothesizing that we are using the wrong indices. And that's the hypothesis testing. So we ended up actually using all 3. And that's usually how to debug in practice. There are more resources, and that's the last slide. Any questions? Any questions before we end? All right, I'll stop recording.